Hello and welcome to this session about Feynman diagrams. You can see on the left-hand side, this is a typical Feynman diagram. What it was developed by Richard Feynman, and it's a way to show subatomic particle interactions. As you can see here, we have time progressing forward, and we have space on the other axis. So there's some idea about how close they get together. Now, one thing to remember here, space is shown, but it is purely a diagram. So it is not an exact indication of the distance involved, although that can be calculated through some other methods. So I'm going to take you through a couple of typical of these and just talk you through. As you can see, we have particles going in this case we have protons, and then we have our interaction taking place, and these two protons are repelling each other. So let's look at this one in a bit more detail. From the bottom, you have two protons moving towards each other. Okay. As we know, the electrostatic repulsion acts between them, and this is an exchange of virtual photon. So the virtual photon means it cannot be detected. If it was intercepted, it would no longer exist, but it's a way of us understanding the process in turn. And this repulsion is indicated by the two photons then moving away from each other. So there's a fairly typical interaction. And we take you through a few of these just to help you understand. So my next one here, this is the interaction of a neutron and a neutrino. Now here we see the neutron approaching and we see the neutrino approaching. Now with this, they're affected by the weak force, so they do not feel strong electrostatic forces. So therefore, we've got to show the weak force interaction taking place. Because they rarely interact, this is quite a rare occurrence, as in this is one which we only see occasionally. Now, we've got the W- boson is exchanged, and this results in the production of both a beta- particle and a proton. We still have the same rules of conservation we've always had. In fact, they're still embedded within this. And Feynman diagrams are the typical way of us thinking about these interactions which we've seen beforehand. So as we can see, this is what happens when a neutrino interacts, causing a neutron to become a proton, and then we have the beta- decay as well. So beta- is a typical electron. We'll look at another one of these. So just to make sure you're aware that the charge is conserved, and that's important. And the reason for that is why it is a negative boson. Okay, beta- decay. So in this case, we have a real decay situation. We have a neutron, and the neutron just randomly gives off, turns into a proton. And for this to take place, again, we have to have a W- boson interaction, and this again maintains the charge. And what we see here is the beta- decay particle coming off, and also the additional antineutrino. Remember, we spoke about the difficulties we had in understanding why there seemed to be a continuous array of energies for the beta- rather than being in specific photons. This is the reason why, because the antineutrino there. So beta+, this is positron decay, and this time we have a proton changing to a neutron, and in this case again we have the same consideration of charge. So protons decaying into a neutron. The W+ boson is produced in this situation. The W+ boson decays into a beta+ positron and a neutrino. Again, where the neutrinos provide the explanation for the range of beta decay. An electron capture now. Here we have a proton. It captures an electron, so therefore it converts into a neutron. In this case, we'll see we have a proton-rich nucleus. And one of the excess protons interacts with one of the inner shell electrons to form a neutron, producing a neutrino. And that are my typical examples of Feynman diagrams. And we're going to practice with a range of these to help you have a better understanding. But memorizing these is really important.